Good evening and welcome back to the channel. Tonight we aren't just looking at another rock in the sky. We are dissecting a physics puzzle that plays out at 70 kilometers per second. If you've been following the headlines, you've heard the name 3I Atlas. It's the third interstellar object cataloged by humanity, after Oumuamua and Borisov. But if you think this is just a replay of those previous encounters, let's look closer at the data, because the story here isn't about where it came from, it's about what it's doing right now, right here in our own backyard. The initial detection was standard. Telescopes picked up a faint point of light, but as we tracked it over several months, the light curve began to misbehave. It wasn't a steady tumbling rock. It was active. We are talking about sustained outgassing of gas, dust, and plasma. Now, comets do this all the time, but 3I Atlas is doing it while moving on a hyperbolic trajectory at velocities of roughly 60 to 70 kilometers per second. That speed is the first red flag. It tells us this object is not bound to our sun. It is a visitor punching through the solar system with incredible kinetic energy. And yet, despite this dominant motion, it is shedding mass in a way that defies simple thermal models. We have photometric and spectroscopic observations, data from ground-based giants and space-based platforms that paint a picture of collimated jets. These aren't the diffuse clouds of gas you might expect from a sublimating snowball. These are directed streams of material shooting out from the nucleus, and this is where the visualization gets interesting. Imagine a bullet flying through the air, but this bullet is spinning and venting high-pressure gas in specific directions. That venting acts like a thruster. It's a natural rocket engine, but the physics governing it are chaotic and raw. This activity has produced what astronomers call an atypical tail morphology. In a standard comet, the tail points away from the sun, driven by solar wind. But 3I Atlas, its tail structure is complex, suggesting that the particles being ejected are heavy, or they are being launched with significant velocity of their own, independent of solar radiation pressure. This contradicts what we previously thought about how small interstellar bodies should behave when they get close to a star. We assumed they would either remain inert or disintegrate. 3I Atlas is doing neither. It is evolving. If you enjoy deep dives into these kinds of cosmic anomalies, where we take the raw papers and break them down, make sure you hit that subscribe button right now. We track these stories as they evolve, and you won't want to miss the updates on this one, especially given what's coming in the later chapters of this investigation. Now, why does this collimation matter? It matters because of the energy budget. For an object to maintain directed jets while traveling at hypersonic interstellar speeds, the internal mechanism must be robust. We aren't just seeing surface ice boiling off. We might be seeing pockets of volatile materials that have been frozen for billions of years in the deep void between stars, suddenly exposed to the heat of our sun. The thermal shock is immense, but the spectroscopic data is showing us something else: plasma. The outgassing isn't just neutral gas. There is an ionized component. This implies high-energy interactions, possibly magnetic, possibly chemical, occurring right at the surface of the nucleus. Here is the crucial detail that separates 3I Atlas from its predecessors. The data indicates that this mass loss is significant enough to alter the object's trajectory slightly, a non-gravitational acceleration. But unlike Oumuamua, Where the acceleration was subtle and mysterious, here we can see the engine. We can see the jets. We can map the plasma. The mystery isn't what is pushing it. The mystery is what is it pushing out. The velocity of the ejected material is the key variable. When a jet fires, the particles don't just sit there, they are launched. And because the parent body, the nucleus, is moving so fast, we have a complex vector addition problem. You have the velocity of the nucleus at 60 to 70 kilometers per second, plus or minus the velocity of the jet. That plus or minus is everything. If a jet fires backward against the direction of travel, those particles leave the nucleus slower than the nucleus itself. They are effectively braked. So, what does this actually mean? It means that 3I Atlas isn't just a lonely traveler, it is a seeder. It is leaving a footprint. It is distinct from a classic dust trail which simply trails behind. Because of the high orbital velocity and the high ejection velocity, the spread of material is massive. We are looking at a cloud of debris that is expanding and shearing apart under the influence of gravity. The nucleus will leave the solar system, never to return. But the material it has ejected, that's a different story. We tend to think of space as empty and interstellar flybys as clean events. Entry, exit, done. But the physics of 3I Atlas suggests a messy encounter. It is dumping tons of material, gas, dust, plasma, into the inner solar system. And this material doesn't just vanish. It has to go somewhere. It creates a structure in space, a ghost of the object's passage. In the next chapter, we are going to look at that ghost, the phantom trail. We need to understand the orbital mechanics that allow some of this interstellar matter to stay behind, trapped by the sun even after its parent has fled back into the dark. Because if that trail exists, and if it stays bound, then the story of 3I Atlas doesn't end when the object disappears from our telescopes. The story is just beginning. As we established in the previous chapter, 3I Atlas is not simply moving through our system. It is actively shedding material via collimated jets while traveling at tremendous speeds. The nucleus is outbound, destined to escape the sun's gravity and return to interstellar space. But remember that vector addition problem we discussed? Here is where the math gets fascinating and where the implications get very real for us on Earth. Let's visualize the mechanics. You have the nucleus screaming along at 70 kilometers per second. It fires a jet of dust and gas backward, opposite to its direction of motion. To an observer on the nucleus, that dust is flying away. But to an observer on the Sun or Earth, that backward-firing jet is subtracting speed from the dust grains. If the ejection velocity is high enough, the resultant heliocentric velocity of that dust, its speed relative to the Sun, drops. This effectively puts the brakes on that specific fraction of the ejected material. While the main body retains enough energy to escape the solar potential well, the dust in the tail does not necessarily share that fate. Jet activity necessarily produces a spread in particle velocities. This means that a fraction of the ejected material acquires lower heliocentric energy than the nucleus itself. So, what does this actually mean? It implies that not all of the release matter must immediately escape the solar system. Some fraction of the dust may remain temporarily bound. We are talking about a phantom trail, a diffuse, extended structure of interstellar material that gets left behind, caught in a gravitational limbo. The nucleus checks out of the hotel, but it leaves its luggage in the lobby. This trail isn't a tight line like you see behind a jet plane. Because of the variety of particle sizes and ejection speeds, the trail shears out. It becomes a complex three-dimensional ribbon weaving through the inner solar system. And the evolution of such a trail is governed by more than just gravity. This is where we have to introduce the non-gravitational forces that rule the life of a dust grain. First, we have radiation pressure. Photons from the sun hit these dust grains and physically push them. For very small, fluffy particles, this pressure can be stronger than gravity, blowing them out of the system entirely. But for slightly larger, denser grains, gravity wins, yet the orbit is modified. Then we have the Poynting-Robertson effect. This is a subtle relativistic drag force caused by the absorption and re-emission of sunlight. Over time, it causes dust grains to spiral inward toward the sun. But here is the crucial detail that makes the 3I Atlas Trail unique: the electrostatic properties of the dust grains. In the vacuum of space, sunlit dust becomes electrically charged. Ultraviolet light knocks electrons off the surface of the grains, giving them a positive charge. Once charged, these grains stop acting like simple falling rocks and start acting like charged particles. They interact with the solar wind, that stream of protons and electrons flowing out from the sun, and they feel the interplanetary magnetic field. This allows for the possibility of density in homogeneities and localized dusty plasma structures. Translating that into plain English, the trail isn't smooth, it's clumpy. Magnetic field lines can trap or funnel these charged grains, creating enhancements, pockets where the dust density is much higher than the average. You might have a vast stretch of empty space and then, suddenly, a filament of interstellar particles held together by electromagnetic forces. This completely changes our modeling of the trail. If we only used gravity, we would predict a smooth, dissipating cloud. But when we add electromagnetism, we get structure, we get complexity. The trail becomes a dynamic entity, breathing and shifting with the solar wind. And this brings us to the composition of the dust itself. If this were a normal comet, we'd expect silicates, carbon chains, standard dirty snowball debris. But 3I Atlas is showing us spectroscopic indications of something else. Something that suggests these grains might respond to magnetic fields even more strongly than we anticipate. The behavior of this trail, this phantom presence, depends entirely on what these grains are made of. Are they insulating rock, or are they conductive metal? The answer to that question determines how they move, how they cluster, and ultimately, where they end up. And as we dig into the spectral data, we find hints of enhanced metallic content. In the next chapter, we are going to look at the metallic signature. We need to understand why this dust is glowing with the spectral lines of nickel and iron, and how that metallic nature turns the solar system into a giant particle accelerator for this interstellar debris. Because if these grains are metallic, the rules of the road just changed. Building on this idea of a phantom trail governed by electromagnetic forces, we have to ask, what exactly is this dust made of? If it were just water ice or simple silicates, the charge on the grains would be relatively low, and the magnetic effects would be minor. But the data from 3I Atlas is giving us a surprise. Spectroscopic indications of enhanced metallic content, particularly nickel, have been detected in the tail. This contradicts what we previously thought about the average interstellar visitor. We often assume they are icy bodies, like Oort cloud comets. But a signature rich in iron and nickel suggests that the grains may behave in a manner that is less typical of classical cometary dust and more complex from both ballistic and electrodynamic perspectives. Why nickel? Why metal? It implies a different origin story for the parent body. Perhaps it's a fragment from a differentiated planetesimal, the shattered core of a dead world, rather than a pristine primordial snowball. But for our purposes today, the origin matters less than the effect. Metallic grains are conductors. When a conductive grain sits in sunlight, its photoelectric yield, the efficiency with which it ejects electrons and builds up a charge, is different from an insulator like rock. These grains can acquire high surface potentials. They become highly charged little capacitors floating in the void. Now, combine this high charge with the interplanetary magnetic field. The solar wind carries the sun's magnetic field outward, spiraling through the solar system. A highly charged metallic dust grain moving through this magnetic field feels a Lorentz force. This is the same force that curves the path of electrons in a cathode ray tube or a particle accelerator. Let's look closer at the data. If the Lorentz force is strong enough compared to gravity, the trajectories of these grains become non-Keplerian. They don't just orbit the sun in simple ellipses or hyperbolas. They can be deflected, channeled, or scattered. This creates a regime where the trail need not be smoothly distributed. In classical dynamics, debris trails spread out over time until they are indistinguishable from the background. But in this electrodynamic regime, local enhancements may exist even if the mean density is low. The magnetic field can act like a lens, focusing the dust into streams or sheets. Imagine sprinkling iron filings on a sheet of paper with a magnet underneath. They align, they cluster, they form structures. Now imagine doing that on a scale of millions of kilometers, with the magnet being the shifting, twisting magnetic field of the solar wind. You get a dusty plasma structure that is invisible to the naked eye, but very real in terms of particle density. This brings us to a question for you all, and I'd love to see your theories in the comments below. If we have interstellar material that is metallic and highly charged, could it interact with our own satellites differently than normal space dust? Does the electrical charge matter when it hits a solar panel? Let me know what you think. So, what does this actually mean for the stability of the trail? It means the trail is resilient. It means that even months after the nucleus of 3I Atlas has passed, these coherent structures of metallic dust could persist, floating through the inner solar system like invisible minefields of micron-sized particles. And this isn't just theoretical physics. We have to map where this trail is going. We know the trajectory of the nucleus. We can model the spread of the jets. And when we plug in the variables for charged metallic dust interacting with the solar wind, we start to generate a probability map of where this material will reside in the coming months. The simulation spits out a date and a location. Orbital geometry implies that in upcoming months, specifically March and April, a specific planet could intersect a portion of this residual trail. And that planet is not Mars. It's not Venus. It's Earth. But the geometry is tricky. The intersection is roughly coincident with 3I Atlas, making a relatively close passage by Jupiter. We have a three-body problem: Sun, Jupiter, comet, complicated by a fourth factor: the electromagnetic fields. In the next chapter, the orbital rendezvous, we are going to look at this celestial alignment. We need to see how the giant of the solar system, Jupiter, might stir the pot, and whether its massive gravity and intense radiation belts act as a shield for us or as a slingshot. The timing is tight, and the margins are razor thin. This connects to the most critical part of our investigation, the timeline. We have established that 3I Atlas is leaving behind a trail of electrically charged, potentially metallic dust. We have established that this dust can form concentrated structures. Now, we have to look at the map. We are looking at a window in March and April. The orbital geometry implies that the Earth could intersect a portion of this residual trail. This isn't a head-on collision with the comet nucleus. That's safely far away. This is Earth passing through the wake, like a ship crossing the ripples left by a speedboat that passed hours ago. But there is a complication. This intersection is roughly coincident with 3I Atlas, making a relatively close passage by Jupiter. You cannot talk about moving dust around the solar system without consulting the landlord. And the landlord is Jupiter. Jupiter is a gravity well of immense power. As the ejecta stream passes near the gas giant, interactions between the ejecta and Jupiter's gravitational and plasma environment could further redistribute the dust. Jupiter acts as a chaotic scatterer. Its gravity can strip loosely bound dust away from the trail, flinging it out of the system entirely. But it can also focus it. Gravity assists work both ways. They can speed things up or slow them down. Here is the crucial detail. Jupiter also has the most powerful magnetic environment in the solar system. If these dust grains are indeed charged and metallic, as the spectra suggest, passing near Jupiter is like walking through a magnetic storm. The Lorentz forces near Jupiter are orders of magnitude stronger than in the general solar wind. This could alter the charge state of particles, stripping more electrons, making them even more responsive to electromagnetic fields, and influencing their subsequent evolution. So, what does this actually mean for the Earth intersection? It introduces uncertainty. A simple gravity model might predict a direct hit by the densest part of the trail. A model that includes Jupiter's magnetic influence might push that stream 1,000,000 kilometers to the left or right. However, the possibility remains. The spread of velocities in the jets, that plus or minus speed we talked about in Chapter 1, creates a very wide fan of material. Even if Jupiter deflects the core of the stream, the edges of that fan are vast. It is highly probable that Earth will cross through some density of this material. We are looking at a rendezvous between our planet and matter that was born around another star. This material has traveled light years, survived the void, survived the heat of our Sun, navigated the magnetic trap of Jupiter, and is now drifting across Earth's orbital path. The timing is specific. As Earth moves through its orbit in early spring, we effectively sweep through the zone where the trail is calculated to linger. Unlike a meteor shower like the Perseids or Leonids, which we encounter at the same time every year because the dust is fixed in a stable orbit. This is a one-time event. This trail has not been circularized. It is a transient feature. Once Earth passes through it, the dust will continue to disperse, dissipating into the zodiacal cloud. This is a fleeting opportunity. The encounter might last a few weeks, peaking as we cross the plane of the 3-eye Atlas trajectory. We need to know what to look for. Will we see it? Will we feel it? If an encounter with Earth occurs, the most probable consequences would be subtle and measurable rather than dramatic. We aren't talking about fireballs raining down and ending civilization. We are talking about changes in the invisible environment of our planet. But as with all things in science, we have to consider the outliers, the less likely but physically permissible scenarios. Because if the dust density is higher than modeled, or if the charge interactions are more intense, the effects could scale up. In the final chapter, the atmospheric test, we are going to outline exactly what those consequences look like, from the humble micrometeoroid impacts to the strange physics of the plasmasphere. We need to understand what happens when a piece of interstellar nickel hits our upper atmosphere at high velocity. It's not a disaster movie script. It's a global science experiment, and we are all living in the petri dish. Given what we now understand about the trail, its composition, and the orbital rendezvous, let's talk about impacts. And I use that word carefully. We are not predicting impact craters. We are talking about interactions with Earth's complex systems. If the encounter proceeds as the most probable models suggest, the consequences would be subtle and measurable rather than dramatic. We would likely see modest changes in the micrometeoroid background. Our planet is constantly bombarded by dust from asteroids and comets, tons of it every day. The 3-eye Atlas Trail would appear as a spike in this background noise. For the average person on the ground, you might notice nothing. Maybe a slightly higher rate of meteors if you are staring at a dark sky. But even that is not guaranteed given the small particle sizes. However, for scientific instruments, this is a goldmine. We could see ionization levels in the upper atmosphere fluctuate. When high-velocity dust hits the ionosphere, it vaporizes, creating free electrons and metal ions. This connects directly to our infrastructure. Aerodynamic drag on satellites in low Earth orbit is real. During solar storms, the atmosphere puffs up and satellites experience more friction. A dust encounter adds a different kind of drag, particle impact drag. It's small, but for a satellite operator maintaining a precise formation, it's a variable that needs to be tracked. But let's look closer at the data for the less likely but physically permissible scenarios. Science requires us to look at the edge cases. Localized disturbances of the plasmasphere cannot be excluded. If the dust is dense and the grains are highly charged, remember? That nickel content, we could see localized plasma instabilities. Increased stress on orbital infrastructure is also a non-zero risk. A micron-sized grain of nickel hitting a solar panel or a sensitive optical sensor at orbital velocities packs a kinetic punch. It can cause pitting, degradation, or electrical shorts if the plasma discharge from the impact bridges a circuit. It is important to emphasize that this is not a prediction of catastrophe, but a testable hypothesis. We are presenting a range of outcomes. The panic button is not on the table, but the record data button should be jammed down hard. Even a null result would be scientifically valuable. If we fly through the predicted path and see nothing, no spike in dust, no ionization changes, no satellite drag, that tells us something profound. It places constraints on the total mass of the ejecta. It tells us our models of interstellar dust evolution are missing a variable. It helps us calibrate the role of electrodynamics in the solar system. 3i Atlas offers a rare opportunity to observe how interstellar material interacts with a well-characterized planetary environment. Usually, we have to send spacecraft billions of miles to study this stuff. This time, the sample is coming to us. The central scientific question is not one of interpretation. We have the theories. We have the equations. The question is whether we will deploy sufficient measurements to turn informed speculation into data. Are we looking with the right radar settings? Are we monitoring the ionosondes? Are satellite operators sharing their telemetry anomalies? This is how science advances, not by knowing the answer beforehand, but by recognizing the moment when the universe is offering a clue. 3i Atlas is that clue. It is a metallic, outgassing, high-speed messenger. And, for a few weeks in March and April, it will be touching our world. If you found this deep dive valuable, please leave a like on the video. It tells the algorithm that people want real, complex science news, not just clickbait. We will be monitoring the atmospheric data as we get closer to the encounter dates. So, stay tuned. Until then, keep looking up.